All right. Hello, everyone. Welcome back to Comp 2150 Object Orientation. I hope that you all had a great weekend. I hope you all had a great weekend. You had no 2150 assignment over the weekend, in theory. But I hear from the back that there's a lot of pain coming out of 2280 right now. I'm sorry to hear that. I'm really genuinely sorry to hear that. I remember learning assembly language, and this is a digression. It's real digression. When I was a student here, we learned not LC3. That's what you're using now. We didn't learn LC3. We learned assembly language for Spark and 68K processors, 68,000 processors. 68,000 processors are like the processors that were in the very first Macintosh, like that little box with the tiny little TV screen in it. That was the kind of processor that was in that. And then Spark was a processor architecture that was designed by Sun Microsystems. Sun has since been gobbled up by Oracle, but they still make Spark processors. And I can't honestly tell you what the calling convention for instructions were, like the order of operations and stuff. I can't remember any of that stuff. But I do remember it was real hard trying to make a list with assembly language. So yeah, I feel you. I'm sorry to hear that.
The content is hard.
Oh, okay.
14 marks.
Okay. Okay. All right. Well, that's also painful. That's also painful. I'm sorry. In terms of announcements, you should have gotten an email from Crowdmark with your test. So if you haven't received that, I've got a couple emails from people saying they haven't got something. So if you didn't get one, please email me. If you have any questions or concerns about the test, so the evaluation, or if there's a mistake or something like that, please feel free to get in touch with me. My preference is by email, because it's really hard to see your test on your phone screen if you come and talk to me in front of class. My preference is by email so that I can actually pull your test up and see it on my own screen. Today, we are going to be talking about the forms of inheritance and the implementation of substitution. We did start to talk about this last week, the forms of inheritance, but I kind of want to just go through it with some examples, and I want to do something a little bit more, I don't know, a little bit more sane. Last week was just bananas. It was bananas, and I think it's a good idea to take a look at some of this stuff again. We're nearly finished with C++, so next class we're going to be taking a look at encapsulation, so like the use of information hiding, so access modifiers. And there's one unique feature in C++, because of course there's some unique feature in C++ called class friendship, and we're going to talk about that, but that's pretty much where we're going to stop with C++. And then we're going to be moving soon onto JavaScript. In the interim, though, we've got some stuff that's just general OO stuff and general software design stuff, and that's kind of where we're at today. The examples that I'm going to show you today in class are going to be both Java and C++, but just to drive examples, so what these things actually look like. So today, we're looking at substitution and the forms of inheritance. I want to start by defining what substitution is again, just so we are all on the same page, about what it is that we're talking about. And then we're going to be talking about the different forms of inheritance. And there are 9 forms of inheritance, and one of them isn't really inheritance, but we'll get to that when we get to it. Inheritance itself, like, a class extends another class. There's only so many ways to do that, but this is a lot more about how you would design classes to be related to each other. So it's less about using the extends keyword and like colon to extend something, and it's a lot more about how you would organize your classes on top of each other and how they're related to each other. For implementation of substitution, the idea here is that we have been doing a lot of like dynamic class binding and stuff. So like, how does our machine actually make decisions about what kind of thing we're looking at? The way that we're going to look at this is in the abstract, though. We're not going to build a compiler. We're not building compilers. I would really love to build a compiler in a course, and that is a course that we have in the books. It has not been offered in many years. we're going to be looking at this in the abstract. So like the consequences of why we can substitute some things with other things and why we can't substitute other ways. All right, so let's initially get on the same page again about what substitution means. So Liskov's substitution principle, this is Barbara Liskov. This is the L in that solid design principles that I talked about quite a while ago. Liskov's substitution principle is effectively, if I have a type, a supertype, and it has subtypes. So I have classes that have extensions, or I have classes that extend another class. I should be able to replace an instance of a supertype. So if I have a statically bound type to a variable, I should be able to put any subclass as the implementation of that. I should be able to assign any subclass, and there should be no observable changes in behavior. So I should be able to replace something, I should be able to interact with its methods, and I shouldn't know that it's a different type than what I have in the static type for that specific variable. That's Liskov's substitution principle. We're going to look at a bunch of different ways that we can have class hierarchies, and the question that we're always going to have for this is, will this kind of class hierarchy satisfy Liskov's substitution principle? So if I have a subtype and a supertype, can I replace that supertype with any implementation of its subtype and have no observable changes in the code that I'm working with? That's the question we're always going to be asking about this. Here are the different forms of inheritance. We're going to step through each of these one at a time. My goal here is to define it, show you an example of what this might look like in code and how to use these kinds of relationships, decide whether or not the code compiles, because sometimes it won't even compile for what we're trying to do, and then finally make a decision about whether or not we can satisfy Liskov's substitution principle with this kind of specific inheritance. That's the way that we're going to approach taking a look at all of these things. All right. So you may have a handout in front of you. You might have a handout in front of you. If you don't, I do have some more copies at the front if you want to play along. I'm always going to ask you this question at the end. Does this form of inheritance satisfy Liskov's substitution principle? And I'm going to ask you to think about it, and I'm going to ask you to show me. And I'm doing like a fancy version of thumbs up, thumbs down today by asking you to show me a picture of the lumpy space princess. The question is always going to be, does Liskov's substitution principle hold for this form of inheritance? If we're using this form of inheritance, if we have these kinds of relationships between classes, does Liskov's substitution principle hold? If it does hold, or it can hold, I want you to show me a happy LSP, a happy lumpy space princess. And if you don't think it's going to hold, I'm going to ask you to show me a kind of angry looking LSP. Did you do your Adventure Time homework, by the way? Okay. The first episode of Adventure Time is on YouTube. That's like how it got started. I'm not sure if Lumpy Space Princess is in the first episode. It's been a really long time since I saw it. I think it's just Finn and Jake in that one. Lumpy Space Princess. No, I'm not going to try to do the voice. Lumpy Space Princess has a very distinct voice. And this is kind of like the default mode of Lumpy Space Princess. She lives in lumpy space. Oh, okay. Pokemon and Adventure Time. This is like university. Yeah, okay. So let's get started. Specialization is a form of inheritance. It is arguably the most common form of inheritance. Specialization is where you've got classes that are representing the is-a relationship. So this is what we've been talking about since like 1020. This is the first time you would have seen something like this, is an is-a relationship. A subclass, so you've got a superclass and a subclass. The subclass may have more things than its superclass. So it might have more instance properties. It might have more methods. It may define more than its superclass. The idea here is that this subclass is specializing what the parent has. We have some common supertype, and then there are subclasses that are specializing that. They're providing a more concrete implementation of something. Here is a hierarchy that's like shown in a linear way where we've got curly braces to group things together. Here's that code, but like code instead of a long linear list of arrows and curly braces. At the very top of this hierarchy, we have this class shape. The only thing that shape does is like 2D geometry. The only thing that shape can have for all shapes is that they have an area. We can calculate an area for any kind of shape. The sided shape builds on, it specializes. It's a specialization of a shape, and that can have both area and sides. A quadrilateral is an actual kind of sided shape, and it can have 4 sides. So this doesn't add anything, but it replaces something. It's still a specialization. Rectangles and squares are quadrilaterals. They satisfy that is a relationship. And they both have their own kind of properties here. So a rectangle extends quadrilateral. It adds some properties, and it adds new methods. A square extends a quadrilateral, and it adds properties, and it adds new methods. A triangle is not a quadrilateral. It's not a 4-sided shape. So we can't really say that it has 4 sides. It is a sided shape, but it's a 3-sided shape. In this hierarchy of classes, I can declare variables. So I can say shape is equal to, and I can assign to that supertype all of these subtypes. So I can say things like new triangle. I can do something like shape is equal to new rectangle later on. And because the only interface that the supertype has, the only method, the only thing that the supertype can do is call area, I can use this interface, this superclass, in the same way without having to make any changes to the code that I have that's using that variable. I can expect them all to work the same way. I can't do the opposite. I cannot do the opposite. I cannot say something like quadrilateral. I can't say quadrilateral Q is equal to new shape, not just because shape is abstract, but because this is not really the way that this relationship works. I can't assign an instance of a shape to quadrilateral or something that doesn't fit linearly in that tree. Okay, so Liskov substitution principle. Can specialization relationships satisfy LSP? Everybody hold up their sign. Everybody. So yes, LSP may be satisfied here. Of course, we could write something that like violates it. We can take this relationship and break it. And we're going to see examples of how to name those kinds of relationships. But in this specific situation, LSP is satisfied. The Liskov substitution principle is satisfied. I can have supertypes, and I can use any of the subtypes in that hierarchy without having to make changes to the implementation, to the code that uses that type. Specialization is like the main thing that we talk about when we're talking about inheritance. Specification is similar to specialization. They are related to each other. Specification, though, is more about a can-do relationship. Specification has supertypes and subtypes, so we've got the same kind of setup here. But the difference between specialization as a big, broad idea and what specification is that specification only specifies behaviors. That means that there's no instance variables in this. There are no instance variables that we're talking about in the relationship. It's just that this kind of object can do this thing. Specifying only the behavior is basically saying we've got a method that we can call, and that's the only thing that we're saying about this supertype. There's a method that we can call. Having this relationship between a supertype that specifies behavior and its implementations is that the subclass in this relationship must implement the behavior. It has to implement the behavior. The way that we have been doing this so far is using abstract classes. So you can see this relationship here. You can see this relationship here. Specification is done in this example by having this abstract class shape. The classes below this all must be able to compute area. There are no instance variables that are part of this type. There's nothing that's an instance variable that's part of this type. It only specifies behavior that we must be able to do. An interface is something that we can use in Java specifically. So this is not something that we can use in C++. C++ does not have this concept. In C++, to do specification, we must use abstract classes or templates, but we're not going to talk about templates. We're not talking about templates in this class. In Java, we have a type that allows us to specify just behavior. The way that that looks is very, very similar to declaring a class. We use public, the access modifier. We use the keyword interface instead of class. We don't have to use generics, and I'm going to do a little example that doesn't use generics here. But the only thing that we can put inside of an interface declaration is method signatures. These are the methods that you can call on instances of this interface. Classes, so class definitions themselves, can implement interfaces using the implements keyword instead of extends. Classes can implement many interfaces. They're not limited to implementing just one. So in Java, we have that singular parent-child relationship. Every class can only have one superclass, but it can have many interfaces. It can implement many interfaces. Let's add a small interface to this shapes example. So because I want this to be able to compile, I'm going to omit the public keyword here, and I'm just going to use interface. But you would normally put public interface, and you'd put this in its own file in the same way that you would work with other Java classes. So I'm going to say interface printable. And I'm not putting generics here. I'm not using angle brackets to specify types. The only thing that I want things that implement this interface to be able to do are print themselves. That's all I want them to be able to do. On interfaces, I am intentionally omitting public on this method signature. I'm very intentionally omitting that. All methods on an interface are public because it's just an interface. It's just methods, and it's just method signatures. So there's nothing to hide. It's just this class that implements this can do this thing, and that's it. To add implements here, here's what I'm going to do. I'm going to go down to the bottom of this hierarchy. We've got rectangle, square, and triangle. Rectangle and square are related to each other because they are both quadrilaterals. So we could have a static type of quadrilateral and we could assign instances of square or rectangle. But there's no common supertype for triangle. There is no common supertype for triangle unless we go even higher in the hierarchy. But I'm not going to do that right now. I can have class triangle extends sided shape, and I can also say that it implements printable. Because I've implemented this interface, I must now add that behavior. I have to add that behavior. I have to add this print method. On my class implementation, I'm going to spell it correctly. I'm going to spell it correctly. In my class implementation, it has to be public. So there's no access modifier in the interface itself, but there must be an access modifier on the class implementation, and it must be public. I'll do something like this. I'm going to add implements printable to my square. And I'm going to add implements printable to my rectangle. I have to add these methods, so I'm just going to say copy and paste. And I'm going to replace the word triangle with rectangle. And I'm going to replace the word triangle with square. OK. So we got these three classes. They are unrelated to each other. They are otherwise unrelated to each other. But now what we've said is that all three of these classes can print. We've specified behavior for these classes. What that means is that in my main method, I can declare a type of variable that is of that interface type. And I can assign anything that implements this interface to that. So I can say is equal to new triangle. I can say printable thing is equal to new square. I can say printable thing is equal to new rectangle. And for each of these, I can say printable thing dot print. So my interface is specifying behavior. My specification relationship here is that the interface specifies print as a behavior. And then everything that implements this interface must actually provide a definition of that method. And we can assign anything that implements that interface to a statically typed variable that has that interface itself. OK? Good, good, good. Is specification substitutable? So yeah, specification is substitutable here. Specification is substitutable. Any of these methods that I call, any of these instances that I'm calling the print method on, they all have to print. Again, we can make this relationship so that it doesn't necessarily do that, and we'll call that something later. But in this specific case, specification does satisfy the Liskov substitution principle. I can use any class instance of that type with its interface type as the type of the variable, call methods on it, and I should expect it to work the same way. So we've got specialization. That does satisfy our Liskov substitution principle. We have specialization. That can also specify our Liskov substitution principle. Another type here is construction. Construction is having an is-a relationship or a class hierarchy relationship where we are extending an existing class to use its structure. So if I'm building a set, for example, I can have that class extend this linked list type because I don't have the ambition to make my own linked structure. I just want to have something that has all of that done for me. And then I can override behavior in this implementing class to do the things that I want to do. Linked list itself has all of the methods and all of the instance properties to keep a collection of things, a sequenced collection of things in a linked data structure. I showed you some code like this last time, but it's different this time. It's different this time. This time I'm talking about a list instead of a countable list or a counting list. Does this code have any bugs? I'm going to really make use of these. I printed 50 of these things out. We really have to use them. So, oh man, this one, happy means no bugs, and angry means there's some kind of bug in here. Can't actually see because they're all just gray blobs. There are definitely some bugs in this code. So here, I've got my set here. I've got my set here. And in terms of a set, it does sort of seem to satisfy this idea that we can only add one thing one time. So let's say my set string, I'm going to have a string set. I'm going to create an instance of my set. I'm going to say string set.add. I'm going to add the same thing twice, okay? And by extending linked list, we got this size method for free. We got that size method for free to tell us how many things are currently in this collection. And if I run that, it says 1 here, just in case you can't see it. It says 1. So it's a set. We only want to be able to add one copy of a thing. I've added the same thing twice, so there should only be one thing in my set right now. Using that part of the interface works correctly. It works correctly. The problem is, by extending linked list, we actually got a lot more than we thought we would get. So there's a bunch of these private methods. There's a bunch of public methods. But then there's all these other add methods that we're getting in this linked list interface that's implemented by the linked list class. So if I do something like string set.add all, and I'm going to make a new array list of strings. I'm going to do it outside here. I can say things like strings.add hello, strings.add hello. And we haven't really violated the interface for list here. There are going to be 2 copies of this word hello, the string hello, in the array list. But if I say string set.add all strings, and I run this again, now it's 3. The expectation was that by getting this add method from my linked list type, I kind of get all of this data structure for free, but what I got was also a bunch of extra interface that I kind of have to care about. The other problem with doing it this way is that I can say things like list string. So list is the interface for lists in Java. I can say list string strings list is equal to new my set. And then I can say things like strings list dot add hello, strings list dot add hello. And there would only be one copy of that in that list, because my set implemented this as you can only add one copy of this thing to the list. Is construction substitutable? So does it satisfy Liskov substitution principle? LSP can't or won't be satisfied here. When I call add on this list interface, I expect multiple copies of the same thing to be allowed. That is my expectation. That's what that interface says that it's going to do. I should be able to have a sequence of things, and it doesn't matter whether they're duplicated or not. I may have changed that by implementing this set, but because I have this relationship of my set is a list, it is a list, jamming that in there and using it does not satisfy Liskov substitution principle anymore. We're good? Any questions? What was the bug? The bug is down here. There should only be one thing in that set after adding this list of strings because they're all the same thing. So if I call add all here, my expectation is that because it's hello, 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 and hello, because this is a set, there should only be one hello in there. There should only be one thing. There should only be one thing in my set. But because it's actually a list, and because I actually have this add all method that I didn't implement, then I have duplicates of something in my set, which there shouldn't be. Oh, how would you figure that out? How would you figure that out? Well, step one is opening the JDK documentation. To be clear, this wouldn't be the kind of question I'd ask you on a test. If I did something like that, I would give you that whole interface for linked list, and then I'd say this implements or extends linked list. I wouldn't say, hey, everyone, whip out your phone and open the JDK and see what the interface is. Yeah, so this code right here, like the 10 lines of code that are there, they're great, they're perfect. But it's the fact that we have this construction inheritance is a relationship with linked list. That's the bug. We're getting a whole bunch of extra stuff that we're not accounting for. Yeah. It would not. It would not specifically for this reason here. So because we are extending linked list, and we're actually like restraining what a list is. We're taking that definition of list and we're just saying you can't add duplicate things to this. That doesn't satisfy what a list is. That doesn't satisfy what a list is. So when you look at the list interface, the idea here is you can just, failed to get sources. You can just add things to it and you'll have a sequence of the things that you've added. It doesn't matter whether they're duplicates or not. So even if you do add implementations of all those methods, it's mainly because you're extending this list structure itself. If you extended a set structure and you called it mySet, then you would probably be able to do list-gov substitution principle. You'd be able to satisfy that. But because we're doing list here and not anything else. Good. Any other questions? So I'm going to ask you to clarify that. I'm going to write out what I think you said. So if you had extends mySet like that, is that kind of what you mean? Yeah, so if you said list my list, and now this is all really underlined in red, new my linked list, with that structure, then that relationship does transitively satisfy the list-gov substitution principle, but the parent mySet class now is kind of breaking that relationship still. Yeah. So this specific relationship, the one that I've got here, and that is what you're asking, just to make sure. Yeah, okay. That specific relationship does satisfy list-gov, but it's like transitively through something that doesn't. Yeah. I'm going to delete that so that we don't have that in here anymore. Okay. So list-gov here doesn't get satisfied. List-gov substitution principle is not satisfied here because we can implement restrictions on what the interface is of the supertype or change behavior of the supertype and then not really be able to use it in place of that supertype anywhere without having changes in the interface itself. The next kind is generalization. Generalization is really awkward. It's really, really awkward. It's really strange to think about. In generalization, you have a superclass, and the subclass is more general than the superclass. So if we've got this structure, we've got a bike class, you extend the bike class and you call it a vehicle. And then you extend your vehicle class and you call it a car. That doesn't make any sense. This is syntactically valid Java. That's syntactically valid Java. We have assigned meanings to what these names mean. We've assigned meanings to what these names are. We can write this code. We can write this code, but it's really very counterintuitive. It doesn't make any sense. It doesn't make any sense to want to do something like that. The only place that I can think of where this is useful is in places where you do not have control over the classes that are being defined on your behalf. The only place where this is useful is in code that comes from a library or code that comes from a framework. And you don't have a lot of experience with libraries or frameworks yet. When you get to Comp 3350, you're going to be doing Android stuff. And Android stuff it uses Java. We're not on the Kotlin train yet. I don't know how much you know about Android stuff, but Google is trying to get people to use Kotlin instead of Java. We're not cool and hip, so we still use Java. And this comes with a predefined set of classes. So a lot of the screens that you see on an Android app, like if you have an Android phone and you open your app, these things are all called activities. There are some very specific activities that come as part of Google's framework for Android. There are some very specific kinds of activities that come with it that you can use to build your app. But you may want to have some kind of a relationship where you are taking that specific kind and then making your own more general version of it so that you can replace that specific kind with your own thing. This is useful when you don't control that base class. You have something that you must extend. You have code that exists that's using a class, but you can't change the code that has been given to you. Generally, and this is what you have always done, if you are in control of the code, you should just use specialization or specification as opposed to generalization. I'm not even going to give you an example of this. I'm just going to ask you the question. If we have something that's given to us and we make it more general, we invert the hierarchy basically, does that satisfy Liskov's substitution principle? Oh no. It can. It may be satisfied in the sense that when you provide your implementation of that class. So you've got this crazy cool library that you're building, and I have, I'm just like desperate to go riding my bike. I'm really lusting over this idea of like being out in the sunshine with the sun in my arms, and I really want to go ride a bike. So I'm going to give you some code. I'm going to say, hey, everyone, I want you to do something that has vehicles, but I'm just going to give you this bike code. If you extend that and you make your own vehicle class, my code, when you give me that instance of a vehicle, still treats it as though it is a bike. I am only calling the interface methods that are part of that bike interface. Because the code that I have written that you are not in control of, because the code that I have written that you are not in control of still treats it as though it is that kind of a type, even though you provided me with a more generalized implementation, this satisfies Liskov's substitution principle. This whole idea is backwards. It doesn't make any sense. This whole idea is backwards. But because my code that you do not control, you can't change my code, you've taken this class and you've made it more general. You've added more properties. You've added more wheels to this thing. Your vehicle implementation has n wheels instead of exactly 2. But my code, because I have defined methods on bike, it only knows about 2 wheels. It only knows about 2 wheels. So you might have added a list of wheels after that, but my code is never going to interact with yours that way. So it's still possible for us to satisfy Liskov's substitution principle, even with this really awkward inverted hierarchy of classes. Okay. But it's also the other way around too. Because you might have added something that says, okay, well, we've got 4 wheels and I'm overriding methods. As soon as you override the behavior that I've defined in my superclass, as soon as you do that, it's possible for you to violate Liskov's substitution principle. It's entirely about how you as the person that's writing this class is building on the thing that I have defined that says whether or not it is or not. So you don't have to feel so bad that everybody was showing no, you can't. It's still may be the case that no, it's not possible. Another type here is extension. We've got a class hierarchy. We have a supertype and a subtype. And the only thing that the subtype does is add new behavior and add new instance properties. The only thing that it does is add new stuff. It doesn't override anything. It doesn't change anything about the base class, about the supertype. It doesn't change anything about the supertype. It doesn't interact with anything that the supertype does. It doesn't use the methods. It doesn't use the properties. It doesn't do anything. It just adds more stuff. If we just add more stuff, we don't change anything, we don't override anything, can I use the subtype in place of its supertype without any changes? Yes, yes, of course, yes, absolutely. If I only add stuff to it and I don't change what that class's implementation does, I don't even like treat it as though it's there, then yes, absolutely. Because the existing behavior that's there doesn't get changed by me, I should just be able to reuse my type in place of that other type, and no code that uses it should have to change. All right, limitation. Limitation is the idea where you take a class, you've got a supertype, and you override it. You extend this class. But instead of adding new stuff to it, you want to take stuff away from it. You extend a class and you override the behavior that you don't want. Here, I've got a list that I want to always be empty. And what I'm going to say here is just assume that I've implemented all methods for a list. So I've implemented all of them. I only have the one here, but all of them look exactly like this. I want this to only ever be an empty list with no elements in it. I don't want it to be allowed to add anything to that list. The way that I do that is either by, in the body of the method, raising an exception. You call this method exception thrown immediately. Or alternatively, you just print, you can't call this method to the terminal. You print out a message. No, sorry, you can't add anything to this list. It's an empty list. Or you just do nothing. In this case, maybe you always return true, or you always return false. You just do nothing to the internal state of the list. Does this satisfy Liskov substitution principle? Very explicitly, it will not, because we've literally just said, all that stuff that this cool list thing can do, no, you can't do it, sorry. But you can use this in place of a list. It's just not going to do anything. It won't be a list. It's not a list. This, in like Java with extends and stuff, yeah, this is an is-a relationship, but what we've done is make it literally an is-not relationship in this specific case. Maybe you've got a list that you don't want to allow adds to. It's not a list, though. Maybe you've got a list that you don't want to allow adds to. You want to initialize it with something, but then you override all of the add methods to do this. You still let it call size. You still let it do like remove. I don't know why you'd want that, but you still allow removal. It's not a list still. It doesn't satisfy what the supertype says it can do and what it should do when those methods are called. So limitation here is very explicitly not satisfying Liskov substitution principle. Variance. Is that you've got two classes that are otherwise basically unrelated to each other, except that they have similar behavior or similar data. But there's no hierarchical relationship between these two things. There's no way for you to say this subclass is related to this other thing as a superclass. There's no way for you to say it. Here's an example. I got a phone in my pocket. Somebody says cake, question mark, pie, question mark, cake, pie, question mark. Okay. I've got a phone. My phone has a screen. It has a display device. Okay. It's got 1, 2, 3, 4, 5 cameras. Amazing. Yeah, it has 5 cameras. It's got a microphone and a speaker. I can talk into it and I can hear music coming out of it. It has ports on it. There's a USB-C port on the bottom of this thing. I have a car in B lot. That's kind of close to where Defoe Library and stuff is, and the law building. My car has a backup camera on it. It's got a camera. My car has microphones in it because I can do like speakerphone and stuff. My car has permanent storage. My phone has permanent storage. I could press buttons on the interface and my preferences get saved in my car. It's got displays. It's only got one display that's like in the dashboard, but it's got a display. I guess there's another one that has just digits on it. I could write classes like public class car, and I can say display D, I can say microphone M, I can say camera C. And then, hey, I don't want to rewrite all that stuff. My car already has that stuff. So I'm going to say public class phone extends car. Cool. Now I don't have to add all those properties. I don't have to add all this stuff that's like public stream, video stream, get video camera stream. I don't have to do that on my car because my phone already did that. I defined this behavior in my phone. And I'm just like, all right, well, they both have the same thing, so I might as well just use an extension relationship and get all that stuff for free. I might as well just use that extension relationship and get all of that stuff for free. Or maybe instead of that, I've got this. And instead of car, I'm going to say, whoops. That I've got a phone that has this stuff in it. Okay, that's still a phone, right? I think, can we all agree that that's still a phone? It's got a camera, it's got a display and a microphone, and I'm just going to extend my phone with my car. This is something that's syntactically valid. This is a way for us to use inheritance. This is a way for us to use inheritance. This is definitely not an is-a relationship. This is not an is-a relationship, but they share the same properties. They share the same thing. So why should I redefine all of that? Yes. It looks like a terrible design choice. I fully agree with you. Yeah, I completely and fully agree with you that this is absolutely a disaster of a design choice. Yes. I didn't say this was a good thing to do. I just said you could do it. I don't think I said it was a good thing. It's not a good thing. Don't do it. I want to reduce code duplication, though. I want to duplicate that code. These people that stand in front of the room keep saying, hey, you have to reduce your code duplication or you're going to get points taken off of your assignment. But these methods that I've defined for my car are going to be the same as they are in my phone. Can a variance relationship satisfy Liskov's substitution principle? Kind of see this right now, like both. It's not an is-a relationship. It's not an is-a relationship. It's a terrible design choice. It is a ridiculously bad design choice. Please don't do this. Don't do this. Yes, sorry. Wouldn't it work? Would it be syntactically valid? Yes, it would be syntactically valid.
But like if the microphone had the method for like taking in information, it would still work on the phone.
So what I'm going to say here is, let's say that we've got car. I'm going to say that car is my superclass, and phone is what extends it. Actually, I want it to be the other way around. I'm going to leave it the way that it is. Oh, stop trying to save it. This is a bad example. I don't even want to give it out. I've got a phone here, and I'm going to say public picture, take picture. So you can take pictures of the phone. It's cool. Yeah, yes, you can take pictures of the phone. You can't take pictures of the backup camera. I don't think anyway. I don't have the ability to take photos with my backup camera.
But like, so we're not concerned about what it is, even if it's literally the same object. We're only concerned about how we're using it.
That's what Liskov substitution principle is, yes.
But then specifying that we overrode the method to be empty. Like, oh right, this doesn't work. Right?
Yes, yeah. So the state of this is, like if I would otherwise have c.takePicture, the thing that we're trying to avoid with this, and again, very emphatically, don't do this. Don't try to use variance to solve this problem. The thing that we're trying to solve is they are identical here. They're identical. They're completely identical in the state that they're in right now. And having that extension relationship saves us from having this duplicated set of features that are part of that. A better solution to this would be to extract the behaviors out of the classes and define a bunch of either abstract classes or, in the case of Java, a bunch of interfaces. The better solution here would be to have something that looks a little bit like this. An interface that says, I can take a picture. An interface that says, can take a video. And on this interface, say something like picture, take picture. And on this interface, say video stream. What did I call this down here? Get camera video stream. Get video camera stream. And if I have this, I would say something like both of these implement can take picture. Sorry, can't take video. This is a car, not a phone. A better solution here would be to extract, stop trying to save this, is trying to extract the behaviors that you've defined in that class and then have interfaces that can be used to demonstrate that these classes can do these things. We've already sort of started to extract some of these behaviors by having these properties that are being used to have the display. An even worse design, so let's go backwards here. Instead of having a display, I have a byte display that's a matrix of, actually, let's call it pixels. Display that's just a matrix of pixels. Yeah, they both have matrices of pixels, but it would be better for us to extract this out into a display class that this thing can have, as opposed to being an is-a relationship. A better thing to do is to use specification or specialization. A better thing to do would be to use containment, or a better thing to do would be to use combination. Containment. This is the promised one thing that's not really inheritance. It's not really inheritance. We're going to call it this, but it's not really inheritance. Containment is this idea of modeling a has-a relationship instead of an is-a relationship. Inheritance and extension is all about modeling is-a. Specification is about modeling can-do, this thing that implements this type can do this thing. Containment is about modeling a has-a relationship, and it doesn't really use extension or interfaces at all. It doesn't use extension or interfaces at all. You might hear the words composition, you might hear the words delegation to describe this. Instead of using this extension relationship, we're going to use composition or containment to specify a has-a relationship. This is that counting list thing that I showed you last time we got together. This is almost identical to the code that I had for that. The difference between the first example that I showed and this one is that I'm not extending anything. There's no extension here. Instead, what I'm saying is that a counting list is something that has a list. A counting list is something that has a list, but a counting list is not a list. It just has a list. And I've defined this add interface, this method add. Do you think this code has any bugs in terms of I want to keep track of all things that have been ever added to this list? Again, we're going to abuse Lumpy Space Princess here. That's terrible. Don't say that. We're going to reuse this piece of paper. We're going to reuse this piece of paper. This has bugs. Angry face. This does not have bugs. Happy face. This doesn't have any bugs. This doesn't have any bugs. We control the interface now. The first time I did this, I said counting list extends list, or a linked list or array list. I used that for construction. I wanted to reuse all of those things that were in that class. The problem with that is that by extending it, we just got all that extra baggage. We have all of that extra stuff that we have to deal with, whether we know it's there or not. There's a whole bunch of methods that are part of the interface for that supertype, and now we have to be responsible for them too. In this approach, when we're doing something that has a list as opposed to is a list, we are defining what the interface for us is. We are saying the only part of my interface, the only thing I can do is add. That's the only thing I can do. The drawback of this approach, while this is a good approach, I'm going to copy and paste this into VS Code here. The drawback of doing this approach is that can't do that anymore. And not just because this is not found. And not just because array list is not found. I can't do this anymore. Not just because I can't infer the argument types for this thing. I can't do this anymore because counting lists doesn't implement that interface. By extending array list, I got that whole list interface. But now I've defined my own interface for this thing that I've called a list, and it's only add. It's only add. So this is no longer a syntactically valid thing to do. I'm not allowed to do this. I can do this. I can say counting list is equal to new counting list. I can do that, but list itself is no longer part of my interface. You control the interface for your type. If you want to implement the list interface, you have to implement the list interface. You got to do everything. Even if it is just delegating to that internal list, you have to do all of it if you want to implement that list interface. That could be pretty painful. There's a lot of methods to implement on the list interface. Is containment substitutable? If I have a class that has a relationship with its properties as opposed to an extension or inheritance relationship, does this satisfy Liskop's substitution principle? The question I want you to ask yourself before you hold anything up is there a relationship here at all, or inheritance relationship here? What are we asking this question about? What can we replace this type with? This is not syntactically valid anymore. That's not syntactically valid. Here, this is syntactically valid. That's syntactically valid. Everybody turn your paper around. Turn it around. This satisfies Liskop's substitution principle in the sense that we're not allowed to substitute these things. We're not allowed to. Liskop's substitution principle says you're permitted to do that replacement, but the behavior is different. This here is you're not allowed to do that replacement. You are forbidden by the language from doing this. Every other one of these examples that I've shown you, and it goes up quite a ways here now, all of these, it keeps going up higher, all of these, no, not all the way to the bottom, all of these, they're syntactically valid. I could put an empty list and I can assign an empty list to a list because it satisfies the list interface, because it implements that interface. It breaks behavior. It doesn't satisfy what the lists interface says it's going to be able to do. Here, with containment, it can be satisfied in the sense that our language forbids us from trying to use this implementation with some other supertype because there is no supertype. There isn't a supertype here. The only supertype to counting list that I have is object. Counting list doesn't extend anything. It doesn't extend anything. This is not an inheritance relationship. This is not an inheritance relationship. I don't even like to call it an inheritance relationship. I'm kind of towing the line here a little bit. I'm towing the line here a little bit in terms of what our department says inheritance is. This is not an inheritance relationship. This is not an inheritance relationship. This is modeling has-a, and this is composition or delegation. It's not inheritance. But I'm towing the line. I'm towing the line. So that's what I'm telling you. It can be satisfied because we're forbidden from replacing it with something that's not a supertype of it. List is not a supertype of counting list anymore. It's not a supertype of counting list. The only thing that it has as a supertype is object. And because this class, if I were to treat it as an object, it would behave as an object, even though it's a counting list, even though it's a counting list. This is not inheritance. It's not inheritance. It's not inheritance. You okay with that? It's not inheritance. That's the problem. It's not inheritance. It's not inheritance. It's composition. It's composition. It's composition. What I'm going to say to you is that this approach, this is a good design choice. This is an excellent design choice. Having something has a relationship with another kind of object is a much better way to get behavior from something else, to delegate responsibilities of that behavior to something else without trying to put yourself into this relationship of I am a list or something like that. This is directly related to this, where we've got this variance relationship between two things that have similar features and can do similar things, but are otherwise entirely unrelated to each other. Having these objects be composed of sub-objects has our relationships that we can delegate that responsibility to is a better design than trying to use inheritance to shoehorn this all together, to try and make this fit into that relationship. All right, combination. This is our last form of inheritance. Combination is an inheritance relationship where we require data or behavior. So specification is we're specifying just behavior. Combination here is both data and behavior. So this is an actual class that we're talking about. Combination is that we've got a subtype that requires data or behavior from one or more class, and that kind of implies that we need to have multiple inheritance. So here's the textbook example. This is literally a textbook example. We've got an instructor, we've got a grad student. These are two separate classes, and we have TAs. And you've got labs where you have TAs. We could say that they are both grad students and instructors. We could say that. So they need to be able to do all the things that an instructor does, and they need to have all the things that an instructor has. They also need to be able to do all the things that a grad student does and have all the things that a grad student has. I really hate that example. I really don't like that example. And if this doesn't convince you to watch Adventure Time, I don't know what will. Because this is also Adventure Time. Like, seriously, we've got lumpy space princesses and dogs that seem to have like really bendable things, and a little talking computer called BMO, and it's adorable. BMO can change his own batteries, where he like pops out the lid, and then he has to put batteries on the ground, and he has to fall backwards onto the batteries so that he can keep going after the batteries come out. Combination is an approach. Multiple inheritance, obviously, it's a thing, right? You can do this in C++. You can extend multiple classes from C++, from a class in C++. However, I would suggest that when you are doing this idea of combination, that you're thinking carefully about what you're actually trying to model with this relationship. With a TA, I would say that this is not a relationship. A TA, a person, is not a grad student. These examples that use people drive me crazy, because if I were to say that I am an instructor because that's my job, it kind of, I don't know, pigeonholes me into being just an instructor, and I'm not anything else. I'm just an instructor. You can use combination to do this, but in languages like Java, we can't. So this might be a better way to represent a has a relationship. A TA is someone that has roles, and the roles that they have are grad student and instructor. Here's our last thing. This is the last place we're going to be able to do this. If we have this multiple inheritance idea, we can extend different classes. Can we replace that type in line with either of those supertypes if we don't do anything other than extend them? Good, good, good. Yes. If we don't change any of the behavior that's defined by the supertypes, even though we have multiple of them, we can be put in place of either of those supertypes, and we don't have to worry about making changes to it. All right, thank you for giving me a couple of extra minutes of your time. I'm going to quickly spin over here. You should at this point be able to describe Liskhov's substitution principle. You should be able to describe different kinds of inheritance by name. So there's a bunch of names. You should be able to describe those different kinds of relationships. You should be able to identify whether or not a type of inheritance satisfies Liskhov's substitution principle. And then we'll do this next class. I'll see you all on Thursday. Bye, everybody.